25 starts with g of x equals x minus 8. G. Whee. Okay, you wanted 28. 25, my bad. 25, 12 minus x squared. Okay. 25 g of x equals 12 minus x squared. Okay, what family of curves does g of x belong to? Is it linear? Is it square root? It's a parabola. So I'm going to say that there's this function called f of x, my reference graph. And so if I'm thinking about, well, how could I rewrite this in terms of f of x? I would say that g of x equals 12 minus f of x. But you wanted the whole thing, not just d. Identify the parent function. You said that was x squared. Describe the sequence of transformations from f to g. Well, it looks like, what do I have to do to this to make this? I have to multiply the y's by -1. I have to add 12 to the y's. So I'm flipping upside down and then shifting up 12. Going to go through that again? So that's what they want from part B. And part C says sketch the graph. Any questions about sketching the graph? Because you have cool transformation graphing skills now. And D, we wrote G in terms of F already. Okie doke. Anything else? Going once? Twice? Yes, please. 33, 33. 33, the graph. Okay, so we've got 2x minus 4 squared plus 3. Let's take a look at that. Ah, don't close. No, don't minimize. Be what I want, not what you want. Why? Because some people find it useful to go watch the videos later on. You might be one of those people. Okay, so 33 was, now I've forgotten it, sorry. 33 was 3 plus 2, x minus 4 squared. Okay, so some people find this order a little more challenging than this order. Do you mind if I use the commutative property to switch those two things? Doink. Okay, so which of these are y transformations? I'm sorry, I couldn't hear you. The 2 and the 3, and that's an x transformation, okay. How will I do that x transformation? Add 4 to all the x's, okay. So I've got -1, 1, I've got 0, 0, and I've got 1, 1. And I'm going to, you said add 4 to all the x's. You said the 2 and the 3 were y transformations. Eden, is there an order in which I need to do those y transformations? What is that order? That's perfect. That's exactly what you're supposed to do. Thank you for that. Multiply by 2. And so we end up with 3, 2. We end up with 4, 0. And 5, 2. But she said don't forget to add 3 to all those y's. And so now we've got 3, 5, 4, 3, 5, 5. And when I plot those points, I've got 4, 3, 3, 5, and over here, 5, 5. Now, hey, let's do step 4 for a second. Examine the solution. When we think about this original equation, are we expecting a parabola that points up? I am, because of this positive number here. And lo and behold, I've got this parabola pointing up. Any questions about graphing that, Audrey? What was the challenge there for you? Adding the 3 on the y's? Okay. All right. Anything else? Yes. For this one? Oh, well, what family of curves did it belong to? Y equals x squared. Cool. So how about 3 plus 2 times f of x minus 4? Right? I'm replacing these black parentheses and squaring with the f of x notation. So this stuff is inside of f of x. So instead of just writing f of x, inside for that x, I'm plugging in x minus 4. So does this say anything different? It says, look, multiply the y's by 2, add 3 to the y's because these are outside, like Kendall said, and then add 4 to the x's because that's inside. Okay? Any other questions? All right. Fabulous. I'd like to then talk about the miracle of birth. I don't have an alternate activity for you today. Besides, I will say, not unlike the small children who grow up today now with the internet everywhere, where they're seeing all kinds of stuff that I don't know that adults should be seeing, let alone little kids should be seeing, you may in fact find it difficult to hide from stuff like this. So better that we should take a clinical approach to what happens when two functions love each other very much. Here are two functions. When two functions love each other very much and they feel that the time is right in their relationship, they sometimes decide, as these functions will for us today, to make little baby h of x. I don't know why they chose that name. I guess they could have chose j of x or m of x, but they went with h of x. And why are you saying of x? Because they're the x family. So, okay, little baby h of x. Now, we perhaps, based on our education, formal and informal, may have a sense of how humans reproduce. Functions, a little bit the same, a little bit different. Function reproduction can come in lots of different forms, but perhaps the most common and expected looks like this. So how am I supposed to carry out that reproduction? What happens? You ever seen any of those movies from the moment the egg is fertilized with the sperm and then you see the cellular division happening and then suddenly there's this baby? Well, it's not suddenly. We're going to do that with this loving experience as well. We're going to look at this down to the cellular level and see how baby h of x is made. But first, let's see if we can get to know baby h of x. First of all, f of x contributes some stuff to it, and g of x contributes some stuff to it. And we do that algebra thing called combining like terms, and we see baby h of x. Does baby h of x look like its parents? In what way? They have an x. Good. It'd be really kind of freaky if two x's got together and there was suddenly baby p. That would be weird. I agree. I wouldn't expect that. Alien abduction time then. Okay. I notice that mom is a linear function. Dad is a linear function. And little baby h of x is also a linear function. That's kind of nice. Yeah. Domain of mom. Gabe, what's the domain? All real numbers. Domain of dad. Allison? All real numbers. And what about the baby? All real numbers. Looks so much like. I mean, there are little differences. Look, it does not. It's got kind of mom's nose, but mom's got a different slope. And I mean, it's not Exactly, but it kind of looks like each of the parents in their way. Look, here's a minus b, here's a minus b. It's not the same minus b, but we don't want to grow a clone. We want them to be their own person. So here too we see this function. But I mentioned that we could see this reproductive act more granularly, more completely, more on a cellular level. So let's do that now. Let's have an enormous t-chart with x, f of x, g of x, and little baby h of x. Now I'm just going to pick some random, easy to work with x values for this process. And I'm going to plug in a -1 into f of x. Okay, so I plug in a -1 here. F of -1 is -1 times 2 minus 5 is -7. And I could plug that -1 in over here. And don't forget, minus a -1 would be +1. And so I'd have 4. And then what's baby h of x? Well, we know that baby h of x is made by f of x plus g of x. So I'm going to take this f of x number and this g of x number. I'm going to add them together. And I'm going to get -3. And I'm going to plug in a 0. And here I'm going to get a -5. And here I'm going to get a +3. And little baby h of x comes from adding these two together. And so I get a -2. And then I plug in a 1. Woo-wee. And I get -3. And I plug in a 1. And I get 2. And then if I add these together, I get -1. And then perhaps we could just use the pattern, the linear pattern in each case, to figure out what f of 2, g of 2, and h of 2 would be. This would be -1, this would be 1, and when we add them together, this would be 0. Okay, cool. We can see baby h of x being built cell by cell by cell at every different point on its body, right? What did we just watch here? At this point on baby h of x's body, Mom gave it this, Dad gave it this, we added them together, and that made that part of that baby. At this point on the baby, Mom gave it this, Dad gave it this is what the baby looks like afterwards. And we could do this for all infinity of points on that baby and map each and every one through a table. But we could also do this process graphically. We could draw a graph of f of x. -1, -7, 0, -5, 1, -3, 2, -1. So there's f of x. And we could draw now g of x. What did he look like? He looked like 3 minus x. So there's 3, 0, 3. We had -1, 4. We had 1, 2. And we had 2, 1. And we're saying, hey, when these two lines get together and love each other very much, what does their baby look like? Well, we know the way these functions choose to reproduce is by adding. So I'm going to take this y value and this y value and add them together, and I'm going to get -3. So baby h of x at -1 has this point, -3. And I'm going to take this y value and this y value and add them together. And I'm going to get 0, -2. And I'm going to take this y value and this y value and add them together so that at x equal to 1, we have a value of -1. 1, -1. And then I'm going to add this y value and this y value so that when I get to 2, the y value is 0. And in green, we see baby h of x being born. It's kind of cool. In the homework, they're going to ask you to make baby h of x. And you should be prepared to make baby h of x algebraically. You should be prepared on a table. You should be prepared to do it graphically. To review, graphically, All I'm doing is going to a point, an x value, and taking these y's and adding them together. I'm going to this x value, I'm taking these y's, and I'm adding them together. Any questions about that? Yes. Well, in the homework, they give you the graph, and so you just use the integer values that are given on the graph. But if you were using a table and they didn't give you a table, I would pick some easy to work with numbers. Okay. All right. So we see the miracle of birth here. This is kind of exciting and cool for us. But I got to tell you that functions are, well, let's describe them as creative individuals. That's not the only way functions make babies. Little baby h of x could in fact be born from f of x minus g of x, or for that matter, g of x minus f of x. What's the baby going to look like this time? O'Brien? Now, I want to stop right here. I want to ask you all to put down writing implements and look at what I just wrote. Because what I just wrote is a really common mistake that shows up in tonight's homework. It shows up on next week's test. What's the mistake? Kyla? Yeah, we have to subtract all of g of x. And with these subtraction ones, people just don't do this. And then because of that, they don't distribute the negative to the negative. And then it's wrong, and you and I are both sad. So be watchful in this one in particular. The subtraction, look for the distributing to show up. Okay, good catch, thank you. And so we now end up with 2x minus 5 minus 3 minus a minus or plus x, and we end up with 3x minus 8. Does baby h of x still look like its parents? Sure, it's linear. Yeah, it's got mom's negative y-intercept. It's a little more sloped than mom, but sure, it's poor dad with his negative slope. It's just not running through the family, is it? It's okay. It's all the linear family. That's good. Method number 3. They multiply. Here, though, Gesundheit, 2x minus 5, 3 minus x, 6x minus 15 minus 2x squared plus 5x, or negative 2x squared plus 11x minus 15. Does baby h of x look like the parents anymore? It's polynomial, I guess. Yeah, we suspect the milkman. Okay. But no, really, it's not. This is just genetics. This is just the method of reproduction. How about this? When we think about the domains of the parents, what's the domain again for f of x going to be? Reese, what's the domain for f of x? All real numbers. And what was the domain for g of x, Ryan? All real numbers. And now what about baby h of x? It's a parabola. I can plug any number I want in. All real numbers. So, you know, the baby looks a little funny. You would never tell that to the parents, but you would think it. But we love all the babies. And the baby still has the unrestricted domain of the parents, and that's great. Yes, please. Funny you should mention it, because functions are really creative. But before we get to that one, and yes, that one certainly does exist, but generally we won't address that one in our class. This is the one that I'm concerned about. I guess sometimes you could see it this way. They can still make babies this way too. Doesn't matter what's on top. These functions love each other and they make baby h of x. But I think there's an issue here. Let's imagine that you heard your friend had found that certain someone special and that they decided the time was right to make their little baby. And they said to you, well, I hear there's a toxic waste site down by the airport, and we were thinking of going there to make our baby. Would you say that was a good idea? Gabe might, because that's the way he rolls with his friends, but other of you had a shocked and horrid look. And I bring that up because I think when functions choose this particular method of reproduction, and some others, but this one is our first one to note it, something happened with that baby. That's not linear. That's not even in the polynomial family. Domain, not 3. Uh-oh. You know what that means, don't you? These parents who had unrestricted domains, no genetic predisposition to alcoholism, breast cancer, anything like that. That kid now, though, that kid is suffering. That kid has now got MS. Look, I can't say, and it's not me to judge moral decisions, but I don't recommend this approach because this poor misshapen baby carries now a genetic restriction that its parents didn't have. And why? Simply because of the method of reproduction they used. Why couldn't they have added? Why couldn't they have subtracted? Why did you have to go down this road? This poor baby. But so this child will have to live with this the rest of its life. Now, you've been looking at functions for years and years now, but I don't know that you've been thinking about them in terms of these little babies. I think you've just been callously looking at them as problems to work through. That's very officious and bureaucratic of you. Really, you need to have some compassion. I've been telling you for a while now, you need to spend more time in step 1 and thinking about what's going on and not just doing the math, right? Think about what the implication is here. You can just take this and put it on top of this and bang, you're done. But there's a little baby that comes from that. And that little baby now has a restricted domain. And so that act of reproduction has some consequences to it. We need to be mindful of that. So the choice of method is important when we think about function reproduction. How many methods, Ms. Holguin, do we have for function reproduction so far? 4. And Brian suggested an exotic 5th. But I actually want to turn our attentions to a 6th one. I'm kind of scared of the 6th one. It's a little grim. So I actually, let's look at another family. You know, those people looked a lot like each other. They came from the same background. Let's take a more eclectic urban family. Hey, we don't judge love. The heart wants what the heart wants. And when two functions love each other very much, they can decide to make a baby. But what do we want to say about her domain? Good. His? He's got a propensity for alcoholism. Yes. So when they make baby h of x, even if they use that most conservative method, we're still looking at this child. oh, you've got dad's eyes and mom's face, but what a strange child you are. Um, but notice, maybe more importantly, Reese sees it. Reese, what can you tell me about the domain of little baby h of x? Here you go. Here's my lasting legacy. My father never looked at me the way my son looks at me and points his finger and say, "You're the reason I'm short and fat." And I, of course, point to my grandparents and say, "That's why you're short and that's why you're fat. I just like Cheetos." Um, but here we see it wasn't the method of reproduction, but it was in fact a genetic link. It really was passed from father to child. Uh, this is a very, very durable metaphor because there it is. We need to be mindful of that. I also wanted to ask about this. What would we do if we saw this notation? What does that mean? What does that mean numerically? What does that mean algebraically? What does it mean we're supposed to be doing here? What are we supposed to be doing here when we see that? Who's got a guess? Brian has a guess. Does Wyatt have a guess? Foil? Wow, I wouldn't have thought to foil. What would it look like when you did some multiplying? F of 4 plus G of 4, maybe? Okay. These are the same. How do I find F of 4? I appreciate your candor and honesty. That's hard sometimes. Sean, how do you find F of 4? Plugging what into which equation? Here's F of x. He says to find F of 4, replace x's with 4's. Okay. So F of 4 is going to be 4 squared plus 1. F of 4 is going to be 17. Hey, Wyatt, how do I find G of 4? Okay, and so that's going to be square root of 4, which is 2, and so we end up with 19. Okay. Anyone think of a different way to do this? Yes. We know by definition that baby h of x was made by adding f and g. And so if we want to know f plus g of 4, Brian says that's the same as h of 4. So couldn't I just plug that 4 in here? 4 squared plus 1 plus root 4 and end up with 19 that way? Yep. Either way always works. Okay? Do you have a question about notation, Madison? Yeah. Okay. I had a little furrowed brow. I was wondering. Okay. Good. So will you find this for me and write the answer on your whiteboard? F times G of 9. Uh-huh. Yeah, you're using this F and G. That's a 9. Yeah, F of G of 9, or F times G of 9. Uh-huh. What's that symbol? Symbols are important. Yes, they are. The little dot doesn't mean add them. Thanks. Thank you for noticing that the little dot did not mean plus. You're a rock star. Do you help the people around you?
Is that right?
Yes. 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 How's it going now? I didn't either.
Problem solved.
Good job. 5, 4.
That's why I got on my
Why not? Why don't you have a calculator? Oh, no, I'd forgotten that. Okay. 3, 2. Mariah's almost ready. 24. 1. 246. Now, I have a question for you about 246. We're multiplying them, not adding them. Okay. About 246. There were two ways of doing this problem. Some people plugged in a 9 for F, a 9 for G, got some answers, multiplied the results. But other people did the multiplying, made the baby h of x first, and then plugged the 9s in. And I'm just wondering who did which approach. Who did approach A, they found f of 9, g of 9, and then multiplied? Okay, and did anyone find little baby h of x and plug a 9 in? Okay. Like I said before, both methods always work. One is not better than the other. I kind of think it's good to know about both. Any questions about this? Do you see it now? Okay, great. All right, good. So we can evaluate functions. All right, so I think it's time to talk about the last method that we're going to address in our class. The one that Brian came up with where a function is raised to another function as a way of maybe making baby h of x. So f of x raised to the power of g of x. That is outside of the scope of our class. It certainly does transpire. Calculus students will run into that, but we would save that for the honors pre-cal class that is of our nightmares. Okay, I know, and I will throughout the year. Okay, so here is the last method that we will address for function reproduction, composition. We clinically describe it this way because we would like to minimize the gruesome impact of the graphic nature of the original notation. The old school notation for this, f of x eats g of x. Look, behold here the distended belly on f of x. Really, did you have to eat your partner to make this baby? And yet we know that there are creatures in our world where, you know, we're just going to be doing that eating of our partner, and that's the way we get those babies. And okay, if that's what you're into. But I am glad I'm not choosing that option. So if we go back to our original family, remember f of x was 2x minus 5, and g of x was 3 minus x. And we think about composition to make little baby h of x. Does anyone recall how to do this? How would we carry this out? Owen? Well, it's true. If I were asking a question like f of g of 2, that's exactly what I would do. But I just want to make the baby first. I'm not trying to evaluate the composition. Okay, plug g of x into the x's of f of x. That's what this notation is telling me. Instead of f of 4 like we saw before, that Wyatt had some difficulty with, it's now f of g. And so Owen says, well, if for f of 4 we just plug the 4 in for all the x's, for f of g we're just going to plug a g in for all the x's. So f of g of x, here's my f of x, and in this x spot, I'm going to take g and plug it in. So I get 2 times 3 minus x minus 5, or 6 minus 2x minus 5, or 1 minus 2x. And you know, curiously, though I may be concerned about the choices these parents made to make this baby, where one ate the other one, the baby looks linear like the parents. The baby's domain is just like that of the parents. And so, yeah, okay, I can see that that's something that works for making babies in function land. Any questions about composition? Okay, will you do g of f of x and show me that baby h of x? G of f of x, and yes, I want to use the same f and g. I'll write them over here if you don't have them handy. Remember, we said f of x was 2x minus 5, and we said that g of x was 3 minus x. And please write your answer on a whiteboard. Five, 4, 3, 2, listen to her. 1. Huh. I see a lot of answers that look like this or this. So let's start with these. Are these the same? This says negative 2x plus 8, and this says 8 minus 2x. And these are the same because of the commutative property. So that's great. I like these. This is certainly what I had on my board. But I also saw a lot of answers that didn't look like that. And I'm wondering if any of the people who had this answer can look at this problem and tell me where they think it's possible for someone to have made a mistake. Where's the common mistake place for this? Yes, Ryan? Forgetting to distribute the negative. When I take f of x, this thing, and Madison, plug it in for all the x's of g of x, not multiply it by, but actually take all this and jam it into that spot, it's now going to look like 3 minus 2x minus 5. Oh, but wait. When people do that, they often don't do this. And what happens if they don't do that? They forget distributing. Or they do this and then they don't distribute completely inaccurately. And so they end up maybe with a positive 2x instead of a negative 2x. I have to distribute here. Get 3 minus 2x minus a minus is plus 5. And so I'll have 8 minus 2x or negative 2x plus 8. So do be careful whenever subtraction shows up with function reproduction. It does show up, and people often know how to do this stuff, but make little mistakes from middle school with this stuff, trying to cut down on those. Any questions about this? Okay, then Owen said, I want to evaluate this function. So what if I wanted to know, and this we said was g of f of x. So with this in mind for g of f of x, how can I go about finding g of f of 2? G of f of 2. What do I do to find g of f of 2, Kendall? So you say, hey, find this f of 2 first. So f of 2 equals 2 times 2 minus 5, or f of 2 equals negative 1. And then what do you do with that negative 1? Oh, because you're saying f of 2 is negative 1, so you can get rid of that and call it this. So you're going to take that negative 1 now and plug it into g. 3 minus a minus 1. So g of negative 1 equals 4, which means g of f of 2 equals 4. Okay, that's one way to do the problem. What's another way to do the problem? Sean? Plug what? I'm trying to find g of f of 4. Edra, can you help him? How could you use g of f of x to help you find g of f of 4? Shelby? No, that was that approach that Kendall did with us. No, instead, this is g of f of x already here. So if I want to evaluate this at 4, I'm just going to replace that x with 4. That's interesting. That didn't work. Oh, thank you. I was looking at the answer. There we go. And now it does work. Now it is 4. Phew, like I said, they should always be the same. Whether you build that baby h of x and plug the number in, or as you suggested, and as Owen suggested originally and Kendall just told us, you can plug into the innermost function. Some number will poop out. You take that poop and plug it into g of x, and g of x will tell you the value. So you've got either choice there. Any questions? Okay. All right. Running out of time. Okay. I think it's time to talk about dead babies. Well, it's part of life, isn't it, death? It's a little dark, I know. But we're now going to be CSI dead baby. I can't tell you how many crime shows with murders I've seen in my life. There's certainly more murders I've seen in my life than there are in the real world in the United States each week, which is interesting. But we, in our lab coats, go out to the crime scene there in the forest. Behold, there under the tree, the dead, moldering body of baby h of x. The parents need to be told, if for no other reason than closure alone. 3x minus 2 cubed. Here's little baby h of x. We need to try and locate its parents to tell its parents about the loss of the child. Well, we know in this part of the country that when functions make babies, they make babies with composition. And so our goal is to decompose this situation. There's lots of different ways we could talk about decomposing this situation. I'd like to suggest the easiest way. We know that composition is f eats G. So there I see F with its distended belly, and on the inside of that belly is a little G of X. Let me out. My job as coroner now is to identify the outside function and the inside function. I have here convenient parentheses. I suggest an inside function. I suggest cubing is our outside function. If I make f of x, x to the third, and I make g of x, 3x minus 2, I can take this f of x, this g of x and plug it inside the x's of f of x. So I take this and I put it in there. Will it look like that? Sure. So this is one set of possible parents. Now when you read the directions in the homework for this set of problems, it'll say find a set, because it turns out there's actually an infinite number of sets. We're just looking for the most common set, or one set. Here's another set. This is the most common set, the inside parent, the outside parent. But what if my outside parent was x Gesundheit minus 2 cubed? Let's say this is my outside parent. What would my inside parent have to be? What parent, g of x, would I plug into the x's of f of x so that the result would be this dead baby? Mikhail? You want me to say it again? My goal is to plug g of x into the x's of f of x. Here's an f of x. I want to plug something in there so that the result is dead baby h of x. 3. If I just plug a 3 in, then it's going to look like 3 minus 2. 3x. G of x would need to be 3x in this case. When I take a 3x and plug it in there, then the composition makes this baby. So this is another set of possible parents. Any set of possible parents will be sufficient for tonight's homework. Any questions about that? Fiorella says she's ready for one last whiteboard problem. Here's your dead baby. Tell me who the parents are. You know the parents made love with composition. G is on the inside, F is on the outside. Please tell me who f of x could be and who g of x could be. Look for that outside parent. Look for that inside parent. Five, 4, 3. I'm going to show two answers when I do my board. I'll show the most common one and the second most common one. 2, 1. Most commonly, people choose outside function square root of x inside 2x plus 3. Second most common, outside function is square root of x plus 3. Inside function is 2x. Either one of those will be fine in tonight's homework. Any questions about decomposition? Any questions about how little baby functions are made? Okay. Bookwork tonight. Remember, when you're adding functions, think about adding those y values together.